China may have just taken stealth technology into a completely new era. Researchers claim they've created an ultra-thin, heat-resistant metasurface coating that can shrink radar reflections so dramatically that advanced aircraft might appear nearly invisible to sensors. In this video, we uncover how this material works, how scientists achieve these results, and why this discovery could reshape the future of high-speed aerospace systems. Let's dive into what makes this breakthrough so extraordinary. China's latest materials science discovery centers on a remarkable ultra-thin metasurface designed to maintain its radar-absorbing performance even under extreme conditions. At the heart of this breakthrough is a graphene silica composite developed by researchers from Peking University of Technology, and Harbin Engineering University. Their goal was ambitious: engineer a fabric-like material that remains flexible, extremely heat-resistant, and highly effective at absorbing electromagnetic waves. The result is a membrane only 0.1 millimeters thick, making it one of the thinnest high-temperature radar-absorbent materials ever reported. To build this material, the scientists used chemical vapor deposition to coat silica fibers with graphene. This produced a lightweight, thermally stable graphene silica fiber membrane, which they later refined using subtractive laser patterning. This laser patterning step transformed the membrane into a metasurface, a microscopically structured layer capable of manipulating how incoming radar waves behave. Instead of reflecting to radar receivers, these waves are absorbed and dispersed, significantly reducing detectability. The performance numbers reported in the study are striking. The metasurface withstood temperatures of 1,000 degrees Celsius (1,832 degrees Fahrenheit) inside a vacuum and stayed effective after being heated to 600 degrees Celsius (1,112 degrees Fahrenheit) in open air for 5 minutes. Under airflow conditions of 200 meters per second, comparable to the stresses encountered in high-speed flight, the material lost less than 1% of its radar absorption capability. Even more impressive, integrating this metasurface into an aircraft's thermal insulation structure could lower radar reflections to -42 decibels, a value associated with advanced stealth performance. What makes this development particularly important is the combination of thermal durability, flexibility, and effectiveness. Traditional radar-absorbent coatings often degrade when subjected to extreme temperatures or extended exposure. In contrast, this new metasurface performs reliably under conditions that resemble high-speed atmospheric flight or near-space environments. Its extreme heat tolerance opens applications that were previously impractical, including high-Mach aircraft, hypersonic platforms, advanced drones, and potentially even satellites requiring electromagnetic shielding. What truly sets this metasurface apart is how it solves problems that have challenged engineers for decades. Modern stealth aircraft rely on special coatings that reduce radar reflections, but many of these materials are fragile, humidity-sensitive, or prone to degradation when exposed to high temperatures. Even some of the world's most advanced jets require climate-controlled environments to preserve their low observability features. In contrast, China's new metasurface is engineered for resilience in the very conditions that typically cause coatings to fail. The graphene silica structure provides inherent advantages. Graphene is known for exceptional electrical conductivity and high thermal tolerance, while silica fiber offers strength and flexibility. When combined, they create a fabric-like membrane that does not crack or peel easily. The laser pattern design enhances electromagnetic absorption by forming a tunable surface, allowing the material to respond effectively across various radar frequencies. This tunability makes it adaptable for multiple aircraft shapes and mission profiles. Another remarkable feature is its ability to maintain efficiency even under fast airflow. When tested at 200 meters per second, simulating intense aerodynamic forces, it retained almost its full radar absorption capability. Many traditional coatings degrade significantly under similar stress because airflow can strip or erode layered materials. This durability hints that the metasurface could be integrated into aircraft areas that experience significant heating or airflow, including leading edges, engine inlets, or surfaces exposed to shock heating during high-speed flight. Its heat resistance also unlocks opportunities for platforms beyond conventional stealth aircraft. Hypersonic vehicles, for example, experience extreme surface temperatures due to air compression. Most stealth coatings cannot survive such thermal loads, limiting the use of radar-absorbing materials on vehicles traveling at high Mach speeds. Since this metasurface remains effective at temperatures above 1,000 degrees Celsius, it could enable new classes of high-speed systems that remain difficult to track across long ranges. Beyond aviation, the material's electromagnetic absorption capabilities could support satellites and high-altitude platforms requiring protection from electromagnetic interference. Researchers even suggest applications in advanced drones and adaptive shielding for onboard electronics. In short, this metasurface strength lies not just in one impressive capability, but in the combination of thinness, adaptability, durability, and high-temperature performance, qualities rarely present together in a single stealth material. This breakthrough matters because it restructures what is possible in modern aerospace design. For years, one of the biggest limitations in stealth systems has been maintenance. Many existing stealth aircraft have coatings that are costly, time-consuming, and sensitive to environmental exposure. These coatings often need frequent reapplication, and aircraft must be serviced in controlled hangar environments to preserve their effectiveness. This creates logistical and financial burdens for any country operating a fleet of stealth platforms. The newly developed Metasurface challenges these limitations. Because it is flexible, durable, and highly heat-resistant, it promises a major reduction in the maintenance demands typically associated with radar-absorbent materials. A lighter maintenance footprint directly increases operational availability, allowing aircraft to fly more missions without extended downtime. This efficiency could influence how future aircraft fleets are structured, enabling countries to scale advanced systems more easily. The potential impact extends further when considering next-generation aerospace technologies. High-speed aircraft and near-space platforms operate in environments where temperatures can exceed the endurance limits of traditional coatings. Since this metasurface survives such conditions while retaining its electromagnetic properties, designers can incorporate stealth features into platforms that previously could not support them. This includes hypersonic gliders, high-Mach reconnaissance craft, and new categories of long-endurance drones. The research also hints at broader multi-domain applications. With electromagnetic shielding abilities, the metasurface could be used to safeguard sensitive components in satellites or high-altitude systems exposed to radiation and electromagnetic disturbances. This expands its relevance beyond aviation into the domain of space technology. Perhaps the most significant strategic effect is how this discovery encourages new design philosophies. Instead of treating stealth as a delicate surface coating, engineers can now imagine integrating stealth into structural layers, enabling more creative freedom in shaping next-generation vehicles. The material's tiny thickness also means it can be layered or combined with insulation materials without significant performance penalties. If you enjoyed exploring this breakthrough, don't forget to like, subscribe, and stay tuned for more deep dives into the technologies shaping our future. Thank you for watching. See you next time.